So the Department of Material Science and Engineering is very happy to sponsor this webinar, where we'll hear a few snippets from various folks on scientists that have made a variety of different contributions to the field of material sciences and even beyond. So I'm going to have the pleasure of kicking things off. I want to highlight two folks, Professor Urara Hasegawa, as well as Professor Xiaotian Li. I will say that we have highlighted these folks rather recently at our Women's History Month webinar. So I encourage you to take a look at that. We have the recorded video, the contributions and so on. But very briefly, I want to make sure to point out that Professor Hasegawa is an assistant professor in material science engineering here at Penn State. And she's done very nice work in developing clever approaches using polymers, not only for drug delivery, but also to be able to control and measure bioactive signaling of, for example, small molecules. Non-traditional small molecules, I would say, that don't always have been in the past recognized to play a significant role in biology, things like hydrogen sulfide and so on. But nevertheless, she has demonstrated she can not only change some amount of the biology that takes place within the cell regulation and fate, but also in terms of getting an idea of how those biological systems operate. And then Xiaotian Li is an assistant research professor as she manages the multifunctional materials manufacturing facility here at Innovation Park. She has made many contributions in terms of articles, presentations, and has been cited many times. And she's an expert on piezoelectric micromotors, on basically how to make measurements on piezoelectric materials. And in particular, she's done a lot of very nice work in terms of developing things like tunable piezoelectric transformers. All right. So again, I hope that at some point you'll take the time to take a look at some of their more in-depth highlights at our Women's History Month webinars that are up on our website. But with that, I'd like to go ahead and move forward and introduce our next speaker, Professor Suzanne Moni, so she can give her highlight.
All right, thank you. I chose to highlight my PhD thesis advisor, Professor Y. Austin Chang, who's also was the postdoctoral advisor of Professor Zikui Liu here at Penn State. And Austin Chang's life is recorded in a biography that his wife Jean commissioned after his death. So looking at the biography, I learned even more about him. He was born in Henan province in China in 1932 during a very turbulent time. It was the Second Sino-Japanese War leading into World War II. There were a couple of years with famine, and also it was a time of the rise of the Chinese communist forces who actually attempted to kidnap him at one point, and he was in hiding for 6 months. So his childhood was very challenging, living in a traditional earthen shelter with no running water or electricity. And he didn't begin his formal education until age 13 when he went to Hong Kong for high school. And then he came to the United States for college. And he ultimately earned his Bachelor of Science in Chemical Engineering at the University of California, Berkeley. He earned a master's in chemical engineering at the University of Washington. And then he wanted to get a PhD. And there are letters in this biography exchanged between him and his wife. And he told her he said she was the first person he told he wanted to get a PhD. And he wasn't telling anyone because he was afraid he would not succeed. But in fact, he succeeded very well, and he earned his PhD with Ralph Hultgren as his advisor, who was one of the first students of Linus Pauling. After he finished his degree, he worked for a while in the aerospace industry, and then he joined the faculty at the University of Wisconsin-Milwaukee. Eventually moving to the University of Wisconsin-Madison, where he was department chair for 11 years. And that was the time that I was in his research group. At that time at Wisconsin, there was a kind of controversial discussion going on whether the Department of metallurgy and mineral engineering should become the Department of Materials Science and Engineering, which was something he thought was a good decision because there were many more materials that he could think and everyone could make an impact studying. And eventually, through negotiations and discussions, the change was made. Later in his career, he became a member of the National Academy of Engineering, a foreign member of the Chinese Academy of Sciences, a member of Academia Sinica, which is in Taiwan. He was very proud and delighted to be elected president of TMS. And he has a successful spin-off company, CompuTherm LLC, which was led and is still led by some of his postdoctoral researchers. So these are some of the main bullet points in his career. And then I thought I'd talk a little more on the next slide about his work. In his biography, several people refer to him as the father of phase diagrams. And Professor Leo Brewer at Berkeley referred to him as the greatest American thermodynamicist since J. Willard Gibbs. So those are very high compliments. He thought about thermodynamics and kinetics, often in very original ways, touching on problems for structural materials and electronic materials, magnetic materials. I just grabbed a few figures and I won't go through and give a lecture on them, but on the left, he's looking at tin telluride and understanding the point defects over the very narrow compositional range that it exists and how that impacted the vapor pressure of tellurium over the tin telluride. He looked at a lot of multi-component systems, and in the second picture from the left, we're seeing some liquidus projections of 3 constituent ternary diagrams to study an aluminum-rich alloy and its solidification. I put one of my experimentally determined phase diagrams for how nickel behaves with indium and phosphorus because I studied nickel contacts to indium phosphide as a student. There were many phase diagrams for lead-free solders and other electronic materials that the group developed. And he was also very interested in combining an understanding of thermodynamics with an understanding of kinetics. And one very interesting problem he solved was how to take 2 pieces of material and put them together. This was molybdenum 2 carbon and silicon. And as they interdiffused, this layered stack of reaction products formed, molybdenum disilicide and silicon carbide. And it was really puzzling. How could this stacking sequence just repeat itself over and over in a diffusion couple? But with some good understanding of the intrinsic diffusion coefficients in each phase and an activity diagram, another type of phase diagram, he was able to explain how these layered structures could form. He was a very good teacher, and I put a picture up of his textbook. He was actually very reserved, and he was kind but quiet, and he asked his students for their opinions a lot. He practiced his talks in front of us, and he gave many of us his proposals to read and proofread. And it might sound like he wasn't confident asking for all that input, but actually he was both sharing the content with us and getting a little bit of help. He didn't need a lot of help. He was a really good communicator. He could organize the ideas to explain an argument in a very logical way. So that would be one last thing. In reading his biography, I also learned that he had a strong belief in equality of all people. We see that in some letters he wrote to his wife before they were married, and a lot of respect for women. And he was very generous, donating money to impoverished people in China, his wife's liberal arts college in the US, and eventually chairing a professorship at the University of Wisconsin. So there's an awful lot to respect and admire here, and I'm glad I had a chance to say something about Austin Chang.
Many thanks for that wonderful highlight. Very much appreciated, Suzanne. Next up, we have, oh, my apologies. Next up, we have Yuchen Hao, who would like to highlight Kai Wang. Yuchen, it's all yours.
Thank you. Hi, everyone. This is Yuchen Ho from Dr. Shashank Priya's group. And here I want to highlight Dr. Kai Wang. Kai is currently an assistant research professor in our group. And Kai earned his PhD from the University of Akron in 2017, and he joined Penn State in 2018. And he now managed the solar module application and characterization facility in the Energy and Environmental Lab. And Kai is a really outstanding researcher in the field of perovskite and organic semiconductors. And to me, he's also a great mentor. And we have do a lot of very interesting research projects together. And Kai likes traveling, hiking, and cooking. And in terms of research, Kai has very great achievement. He has authored and co-authored over 80 journal articles, and he have been cited over 3,500 times. And so here I just list some of his great contribution to the field, like he contributed to the development of novel organic and perovskite semiconductor materials, and he did a lot of research to find new physics in this novel highlight perovskite system, and he also tried to develop advanced solar cells and the photo detectors based on these novel organic and perovskite semiconductors. And finally, he also tried to advance the manufacturing technique of these new materials. Next slide, please. Next slide, please.
Mm-hmm.
Thank you. So here I just list some of Kai's research. Like as I mentioned before, Kai's research is expanding from the basic material science to the device level. And from the device, we can see Kai has been working on the solar cells to trying to improve its efficiency and stability. And also he tried to make large area solar modules and also the flexible perovskite solar cells, which is the most advantage of this semiconductor, that it can be made into flexible photovoltaic device. And also on the material science side, Kai has explored some new physics in this new novel perovskite system. Like he have made some discoveries on the conducting age state in the 2D perovskite material, which has been never reported before. And he also makes a lot of technology innovation. Like he has used the perovskite to make some photothermal membrane, and this membrane can efficiently harvest the solar, the heat energy from the solar, solar energy. And also he try to make he innovate a novel perovskite ink, and this ink is very interesting. That this ink can crystallize into the semiconductor film at room temperature without any heating and other processing. And so this can be a very great contribution to the commercialization of this novel perovskite semiconductor material. And finally, Kai has also tried to advance the manufacturing technique of this perovskite material. Like he developed a new chemistry method to synthesize the single crystal of this new material, and also try to use some advanced manufacturing tools like the picosecond lasers and electrospray to make the large area solar cell modules based on this perovskite semiconductor. Yeah, so that's all I have. Thank you.
Thank you very much, Yuchen, for the very nice highlight of Kai's work.
Thank you.
I really appreciate it. Next up, we have John Asbury, who will be highlighting Ching Wang.
Thanks, Enrique. Yeah, it's a real pleasure to get to highlight Ching. I'm going to share sort of the technical and academic highlights first, and then I'll share some personal comments toward the end of the time. So Ching has been, you know, he's been really a very visible figure in the polymer inorganic hybrid sort of composite nanomaterial area, as has some of the just sort of metrics that we use to indicate impact are showing that really some of his work since 2016 is just really dramatic in terms of its impact and visibility. And I pulled out a few papers and just sort of that give kind of a characteristic of that work. Ching hails from first did his Bachelor of Science in Materials in Material Science and Engineering at East China University in Shanghai, Wuhan University for his master's in Wuhan, of course. PhD with Long-Qing U at University of Chicago, and then did some postdoctoral work in Cornell before coming to Penn State. And he's been risen up through the ranks since 2002. Or some of his recent awards, just to kind of give just a little bit of snapshot. He was elected a fellow of AAAS, the Penn State Faculty Scholar Medal, as well as the Wilson Award, both from Penn State. So he's Ching did a sort of a transition, which I kind of relate to, which I'll share in a bit, with from his training. He worked on conjugated polymers, so semiconducting materials, and then when he started at Penn State, he transitioned to dielectric materials, so insulating materials, materials for high density energy storage, as well as kind of related piezoelectric and sort of being able to harvest energy from deformation of materials or causing deformation of materials by application of potential. And so the first sort of upper center paper from an energy and environmental science highlights a really interesting foam that a piezoelectric foam is very compressible and allows for quite efficient conversion of mechanical energy into electrical. Another area that's been really impactful in Ching's work has been in the boronitride nanocomposites, where he creates these layered structures, and sort of it's a little small on the scale, but there's a really nice high resolution DEM image where you can see layers of the hexagonal boronitride that are sandwiched in between polyvinylidene fluoride layers, and they give rise to really high breakdown and high energy storage materials for basically energy storage in these sort of really high energy density capacitors. And then I would invite you to check out a YouTube video. This is on the right-hand side of this screen. YouTube video you can find on his faculty page of a self-healing dielectric polymer. These are the lower portion are just screenshots I took of that video, where he takes a polymer film and he cuts it in half. Okay, and then in the video he just pushes them back together, heats it, and then is able to suspend substantial weight off of that polymer film to show that it has in fact rebonded. And this is sort of a visual representation of maybe what's very interesting in terms of the dielectric properties, where materials that can self-heal from a dielectric breakdown. It's really a really nice work, and as well as a great visualization of that work. So that's sort of, it's a bit of a snapshot. You could go on far more than that, but I wanted just to kind of take a couple minutes to share some personal reflection. So I met Ching early on in my faculty career. This, I guess, was around 2007 or 8, I suppose. And I had also switched fields from my postdoctoral work, for example, was studying water dynamics to inform development of molecular dynamic simulations. And I switched to studying organic photovoltaics and using infrared spectroscopy as a structural tool to elucidate the origins of their properties. So I knew nothing about the field, basically, getting started, except that I could probably inform that. I didn't know anything about the funding structure, didn't have any real relationships with program managers. But I just I met Ching, and we started talking, and he had the background in semiconducting polymers, and so that was a connection. And Ching introduced me to Paul Armistead, whose program we're still funded in, with Enrique as sort of our captain of the Muri ship these days. But Ching just sort of took me under his wing, made those introductions. I realized when I got started, my graduate and postdoctoral advisors were great, but they did zero preparation for what it's actually like to be a professor and lead a group and raise funds and deal with personnel issues and troubled students. And I knew nothing of those things. And Ching was really the first person that I met here at Penn State who was like, hey, you should do this, and these are some good things you should, and I just kind of listened to how he would describe interacting with program managers, interacting with this group, and I just took notes basically and did what he did. And it was really it was great for me, really tremendous mentoring and professional development. I don't think Ching even knew that he was doing those things, but he just did. And I benefited greatly. So I wanted to just kind of just kind of honor him through that, and I'm glad to have the opportunity to do it.
Thank you very much, John, for the very nice highlight of Ching. Very much appreciated. Next up, we have Venkat Gopalan. Venkat, it's all yours.
Yep. Hi, I'd like to highlight C.V. Raman. And of course, all of us have heard of the Raman Effect. And I've been actually looking at the history of how that came about. It's very interesting. So here is Raman in his lab in the Indian Association for Cultivation of Science in Calcutta. And there is a plaque there from the American Chemical Society and the Indian Association for the Cultivation of Science, IACS, that reads, that's on the top right corner, dedicated to C.V. Raman's discovery of the Raman effect in 1928. And he won the Nobel Prize for this effect in 1930. And the plaque was placed in 1998. All right, next slide, please. So his full name was Chandrasekhar Venkat Raman, and he got his BA from Presidency College in Madras. He was born in 1888, so India was a British colony. So and Madras was a presidency, and he was he did his BA. He was very bright, and at 18, he had his first paper in the Philosophical Magazine. By 16, he graduated and finished his bachelor's. But because of his poor health in those days, there wasn't that much of fundamental science in India, and you had to travel to England or to Europe to do advanced studies. And he was not in great health, so he couldn't make the travel. It was by ship in those days. So he just took a civil servant job, and he became an accountant. And he was posted to Calcutta in 1907. And there was probably there was the first institute for basic science called Indian Association for the IACS, the Indian Association for the Cultivation of Science, which had just started, and he literally bought a house right behind it with a door opening into this institute. And in his after his day job, he would go in there and fool around. he started out playing with strings, all sorts of musical strings, to study the wave theory. So he wrote lots of papers on just waves. And 10 years after he joined as accountant, he had published 27 papers on the side. And his name and fame sort of had already arisen. People in Europe had already got to know him, by at least in terms of his publications. And he traveled in around 1921 to England, to London. And there he met some of the giants in the field, J.A. Thomson, Lord Rutherford, and so on. And they had already known him. He got a very warm reception. On his way back on this ship called SS Narkunda, he was watching the Mediterranean Sea and how its color was so blue. And he was, at that time, Lord Rayleigh's explanation was that the water was reflecting the sky, therefore it was blue. And he was just not convinced that that was true. And on the ship, he came up with the theory that just like Lord Rayleigh had explained why sky was blue, air molecules scattering light, and blue scattered more than the other colors, that water was scattering light, and that color came really from that. And he wrote a Nature paper on board the ship, and as soon as it landed, he mailed it in, and there was a Nature paper on that. So that's that's how Nature papers were written in those days, I guess. But anyway, so he came back and he just plunged himself into scattering of light by molecules and liquids. And by 1928, he had discovered the Raman effect. By 1930, he had won the Nobel Prize, and he has won a bunch of other prizes listed below. Next slide, please. Here is a very small explanation of this on the top right corner. And remember, there were no lasers at that time. There was no optics. This is all like homemade stuff. Here, the instrument that he used later on is at the bottom, and one of the first spectrographs he took, the first Raman spectra, is at the bottom left. So literally, he was working with sunlight. If somebody asked you to today do Raman spectroscopy with sunlight, even the best experimentalists will struggle today. But in those days, like Michael Faraday time and so on, these guys were really self-made. They started from scratch and built things. So here, sunlight comes. He had a violet filter. The violet filter shines on some liquid. I'm talking about the top left, like that big blue circle. It scatters back the violet, but then he filters it out, and he sees some other colors coming through with slightly lower frequency, in this case, green. And all his early measurements were, they didn't have high quality spectrometers. It was all very visual. And later on, he got better and better at focusing sunlight and seeing this effect and making sure it was not an artifact. And eventually, he also kind of knew that this was a quantum phenomenon, that this was actually one of the proofs that quantum theory of solids was correct. Now, later on, lasers were invented and FTIR came up, and MCL has an excellent Raman lab, excellent Raman spectrometers in imaging, imaging equipment. Now, as you can see, a number of industries use this. It's an instrument that all of us in material science use almost on a daily basis. Many of us, for sure. Next slide, please. I just decided, because we were doing Raman spectroscopy, we are currently, so I got a slide from Hari Padmanabhan, a graduate student here at Penn State. In my group, we are studying, it should be MNBI2TE4, the 4 went missing there. But here is a spectrum of the Raman spectrum from this compound. It's a topological insulator. Crystals were grown by Ziqiang Mao. You see a bunch of peaks. All of these peaks are representing different vibration modes in this crystal. The atoms are vibrating. They are different vibrational modes. You can assign them to different symmetries and irreducible representations. So these are all individual dances of atoms, coordinated dances of atoms in this crystal. The interesting thing I want to point out is some of the subtleties. There is also magnetism you can pick out from here. The blue and the red are at 0 Tesla versus 9 Tesla. You see how there's a little shoulder where it says spin phonon coupling. There's a little shoulder. And then there is a peak in the red that comes up at the very low end around 10 wave numbers. Those are magnons. Those are spin waves that are dancing around, and they are influencing also the lattice vibrations. If you pick up on that, on the top right, you can see the gray line is the magnetic order that's evolving as a function of magnetic field. And the blue dots are this change in the shoulder around where the spin phonon coupling is written. You can see it follows very well. So it's not just lattice vibrations. You can also learn something about magnetism by Raman spectroscopy. It's just a very nice example of very current work going on in the lab. It's not even published yet. It's in review. Okay, next slide. I just want to end with saying that he won the Nobel Prize. His nephew, C.V. Raman's nephew, is Subramaniam Chandrasekhar, and he also won the Nobel Prize. He was an astrophysicist. He was at University of Chicago. He is an Indian American, although C.V. Raman was, all his education, all his work was in India. But Chandrasekhar Subramaniam was an American, brought up in India, but studied here. And he's famous for the Chandra Observatory out there in space, through which we do X-ray imaging of the skies. He's also known for the Chandrasekhar limit, the maximum size of a white dwarf before it can collapse. It will collapse to form a neutron star or a black hole. And you can see a whole bunch of other things that he discovered. He was very prolific. Okay, that's all I have to present today.
Thank you very much, Venkat, for the very nice highlights, both of Rama and Chandrasekhar. Next up, we have Clive Randall.
Good morning, everybody. It's a great honor to be able to say a few words about Long-Qing Chen. And I remember when Long came to Penn State, and he was hired by a department head at the time, Dick Tressler. I remember him saying to me, he says, "We just hired one of the brightest people that we have in a generation." And I always thought, okay, well, that's really fantastic. And the words of Dick Tressler, as I was preparing for this presentation, really came home. And I think that we have had a generational scientist in the area of thermodynamics at Penn State. In fact, we're very lucky we actually have two. But Long was the first to arrive, and he arrived here after first being educated in China, but then transitioning to the United States at Stony Brook, did his PhD at MIT, and then I think he would admit that both the MIT experience and also his experience with Xiaotian at Rutgers was incredibly influential to his time. In fact, at his time at Rutgers, he worked on the ordering of lead magnesium niobate, which is and they were discussing some work that I had done for my PhD on TM analysis of that ordering. And he was then able, with his phase field modeling approach, to then be able to predict the sort of structures that I had seen in the microscope. And in fact, in the nature of structure property relations, we need theorists to always work with experimentalists. And Long has done this not only just with his colleagues here at Penn State, but he has also done this with many, many colleagues around the world. And he now has an enormous number of citations. He is arguably the greatest disciple of the phase field approach, thermodynamic approach. And this approach, thermodynamics, combined with also its derivatives in the time domain, allow you to look at all sorts of things that are important, from precipitation coordinate, coarsening, grain growth, crystal growth. He's looked at dendritic growth. He's looked at more recently in the ways of even applying electric field and an AC electric field to then being able to make PMN PT crystals transparent. And this has profound implications in terms of potential acousto-optic medical devices. He's also worked with Venkat and Ramesh at Berkeley on these skermions, these metastable forms that can be quenched in, that then create these vortices of polarization stabilized by localized charge. And so his approach has allowed us to look at not just the traditional ideas of structure-property relations, but also metastable states. And I think that has been an absolute joy. And I will say that he's one of the most modest, matter-of-fact, brilliant persons that I've had the pleasure to meet in my generation. And I think that all my colleagues that have worked closely with him would reiterate that. And even as we discussed making this presentation, that modesty came across, and he didn't want to be honored. And so, sorry, I've done this, but I'm also obeying and honoring you in regard to the second slide. So, because Long really wanted me to honor Chen-Chi Li, and she's also a Penn Stater. And let me tell you a little bit about her. And so there's a number of early Chinese scientists that came to Penn State. Another one is Yaoshi. And gosh, phone's going off, sorry.
Yeah.
Very sorry. Yeah, so Chen-Chi Li was born in 1942. She studied physics at Fudan University. And then the Cultural Revolution in China came along. And for academics, this was a severely awful situation. They got taken out of academia. They were asked to accommodate to the communist ways and basically be on farms and to work with your hands and to appreciate the all-in philosophy of the communist movement at that time. She did this for 2 years on an army farm. Then she went to Shanghai Institute and then became a visiting research scientist here at Penn State, at the Materials Research Lab, working with Eric Cross. Yaoshi also worked with him at that time. She wrote a couple of papers. I remember reading them even when I was a student back in England on the lead-scandium niobate ordering system, turning it from ordering that B-site order to change it from a relaxer ferroelectric to a normal ferroelectric. After leaving Penn State, she went back to the Shanghai Institute, where she was made vice party chief for that very important ceramics institute, and then gradually rose through the government to extremely high levels. The national education head of the Minister for Education for China in 1998. She was then also the state counselor for not only just education, culture and sports. And then when the Olympics came along, she was then the governor of the Beijing village. She's now retired, but she has probably risen to the highest political ranks over the largest population in the world of any of our alumni. And Long, and I think all of us that have a connection to MRL and ferroelectrics all know Chen-Chi Li and realized that she was probably the largest influence of education in any country in the world because of her political statements and political vision for China, and was one of the first Chinese to come here after 1971, after Nixon went to China. And the impact that her educational vision had probably explains a lot about the high level of education that now exists in China. So thank you very much.
Thank you very much, Clive, for those nice highlights of Long and Chen-Chi Li. All right, next up we have Na Lu. I hope I said that correctly.
Yes.
Na, all yours.
Thank you. Hello, my name is Na Liu. So working in Dr. Priya's group. So it's my biggest honor to highlight my colleague. I also want to say he's kind of my mentor, Dr. Poudel. So he is now is an associate research professor in Dr. Shashank Priya's group. Bad is a highly reputed scientist in the field of thermoelectric. He's a pioneer in the field of nanostructured thermoelectric materials. And he holds a PhD degree in physics, specialized in nanostructure. Not going to this slide, yeah, but it's okay. In the nanostructure thermoelectric from Boston College University in the US. And then he has more than 15 years of experience in thermoelectric material research and product development. His expertise include not only nanomaterial synthesis, also the characterization, as well as the device design and the manufacturing about the thermoelectric. And he holds over 20 patents and pending in the field of thermoelectrics. And also he published over 25 scientific articles in various journals, including the Science and the Nature Materials. He's also a recipient of R&D 100 Award in 2008. He was from Nepal, and he completed his bachelor and master in Nepal in 2001, and then he came to US to start his I would say his career in the thermoelectric field, and from 2007, and his PhD was complete in the Boston College in the field of nanostructure thermoelectric. And then after his completion of his PhD degree, he came to the in the company called GMZ Energy, and he works there as a various roles from 2007 to 2013. During his stay in this GMZ Energy company, this is a startup company, so he helped to develop the thermoelectric materials and products such as solar thermoelectric generator, it's called like STEG. And then from in between 2013 and 2016, he moved to another company, Evident Technologies in New York City, as a director of R&D and CTO at this company. So he led the technical team in developing the high temperature thermoelectric materials and the devices, and also launched the thermoelectric generator products. And after that, he worked at Nimbus Materials in California in between 2016 and 2017. And he worked as an R&D director, developing the flexible thin film thermoelectric products for body-powered thermoelectric generator for consumer electronics and sensors. And since 2017, he started to join the Dr. Priya's group and to build up the thermoelectric lab, and also to monitor the people here. And next slide, I would highlight his achievement, his big contribution to the thermoelectric field. So from this, the left up image, I would introduce his work about nanostructured, thermoelectric development. So Dr. Brad Poudel's main research here is in thermoelectrics. The thermoelectrics can convert the waste heat directly into the electricity. This conversion efficiency of this thermoelectric device is determined by the dimensionless figure of merit, which is called ZT, along with the temperature difference. The nanostructured engineering for thermoelectric technology was proposed to significantly reduce the thermal conductivity of these thermoelectric materials so that this JT performance can be enhanced. Back to time around the 2000, the ZT in a bismuth telluride-based bulk alloys has remained around only one for more than 50 years. During Dr. Brad Poudel's PhD stay at Boston College, he successfully realized the nano crystalline bismuth antimony telluride bulk alloys. And can achieve a peak ZT of 1.4, which is 40% improvement as compared to the state-of-the-art result at that time. So this breakthrough was published on Science and promote the real application using the bismuth telluride-based thermoelectric materials in waste heat recovery, air conditioning, and also the refrigeration application. In this slide here, I would like to point his another contribution to the thermoelectric field. So this is about this field is about this high performance flat panel solar thermoelectric generator. This is accomplished in 2011. He made a great breakthrough using a thermal concentration in a flat panel absorber configuration, as shown in this figure, and which can convert the solar radiation into the heat and thermally concentrates it onto the thermoelectric element, creating very large temperature difference across the thermoelectric device. At the end, 7 to 8 times higher conversion efficiency as compared to the previously reported. The best value for a flat panel solar thermoelectric generator is achieved, resulting from this innovation design in that exploit the high thermal concentration in an evacuated environment. Besides that, so he besides always dedicating into the new thermoelectric materials and the technology development, he also made a great contribution to bridge the gap between the thermoelectric material and the real device application during his career in industry, serving as a CTO and R&D director. This is substantially demanded to promote the thermoelectric technology into the real application. And after he joined the PSU from 2017, and he established a world-class level thermoelectric lab taking care of the entire process from material synthesis, processing, characterization to device fabrication and test, which you can barely find the second place all over the world at the same level. So all listed here are far from enough to describe a bad distinguished accomplishment in the science. So next slide, I would to highlight that he's not only a good or excellent science in the as a researcher. He's also very good mentor, and working with him has a lot of fun. His sense of humanity, not humor, and he also the working spirit, and is really making the working atmosphere very enjoyable and very appealing. And so he has some very good, very wise saying during his working time. So this is like you need to enjoy what you do. Make sure that doing research makes you happy and enjoy being part of that process. I never think this as a profession only, but this is also the part of my life. So when you work with him, you feel like the working is not the working. Working is like enjoying the life, and is like you really feel it's a happy thing there. And the second is the confidence. So he said you need to believe that you can do anything scientifically possible. In the meantime, make sure that there is no arrogance in you. And that is, I feel like very significantly when I work with him. And so I always like jump into the new research field. And when you work with him, you don't feel like you are scared that this field I'm not so familiar. And so when you work with him, he can always like make you very confident. You can always say your idea and don't be afraid. And yeah, and the third thing is the humility. He says, understand that you don't know everything. In fact, we know so little. And this way will make you a humble and an open-minded person, which are very important quality of a researcher. Thank you very much.
Thank you, Na, for that very nice highlight of BED. Next up is Chris Ron. Chris, it's all yours.
Thanks very much, Eureka. Very happy to be here today. And actually, it's great to see BED recognized. BED is my associate director for the Center for Energy Harvesting Materials and Systems, who's been doing a great job. So congratulations, BED. And I really like the idea of this webinar as well. I've certainly benefited from collaborations with many Asian American faculty members that we have at Penn State and elsewhere. And I have great research relationships and friendships with members of this community. They've made a huge impact in my career, both technically and professionally. I'm proud to work with our colleagues in our Asian American community this month and every month. So it's my pleasure and honor to highlight Shashank Priya. Shashank grew up in Lucknow, Uttar Pradesh, India, and his family was mostly academics and teachers. I think his father and grandfather were actually educators. He received his bachelor's degree from the University of Allahabad in 1995, and then was accepted into the Indian Institute of Science in Bangalore for an integrated BS/MS in materials science, what eventually became materials science. And this is the most prestigious institution in India, and tens of thousands apply for less than 50 slots. So one of the things our Asian American colleagues have to get through is a very tough process of getting even to the United States. So it's very challenging, very competitive. He graduated in 2000. He had some good job offers in India, but decided to come to the US to work with Ken Xiaotian at Penn State. 3 years later, he graduated, and actually one of those years he was at Urara in Japan, so very quick PhD. And within 6-8 months, he had a job, tenure track position at UT Arlington. A few years later, Virginia Tech lured him away with the early tenure and promotion to associate professor. And he was very successful at Virginia Tech. He was awarded the Hord Professorship in Mechanical Engineering and worked as associate director of the Institute for Critical Technology and Applied Science. And he became well known as a world-class researcher in multifunctional materials, energy harvesting, and bio-inspired systems. And I think the part that impresses me most about Shashank's work is his ability to span fundamental material science to devices. And his group is always making some very exciting, very interesting devices. So during that time, he also managed an IUCRC program at the National Science Foundation. And he was the founding director of the Center for Energy Harvesting Materials and Systems, which now I'm a director of a site here at Penn State, and Ben is my associate director. In January of 2018, we managed to lure Shashank back to Penn State to be our associate vice president for research and director of strategic initiatives. And he's making great contributions, university-wide, to growing our research portfolio, establishing new research collaborations, and helping our faculty to be successful in very competitive research proposal efforts. So I've enjoyed working with him both administratively through our research development roles, and me within the college and him at the university, and technically within the Center for Energy Harvesting Materials and Systems. So Shashank has led a distinguished research career with over 400 journal papers published. He's a world-renowned researcher with a large interdisciplinary research group here at Penn State. I'm most familiar with his energy harvesting work, and the breadth is quite amazing. He's worked on everything from solar to magnetic to vibration to thermal mechanisms for energy harvesting, and sometimes combining multiple techniques in one device. So it's very impressive work. He's a very visible member of the technical community, leading workshops, creating new conferences, including the annual energy harvesting meeting that many of us have attended many times. So we're very fortunate to have Shashank on our faculty. He's come a long way from a quote small town in India to the top of academia. Congratulations on your success, Shashank, and continued health, productivity, and prosperity to you in the coming years. Thanks, Enrique.
Many thanks, Chris, for that very nice highlight of Shashank. Next up, we have Rob Hickey. Rob?
All right. Well, thank you for giving me the opportunity to highlight and discuss some of the major impacts that Professor Mike Chung has made through the years. So what I'll do is, just give a brief overview. So you got his BS in chemistry at Chung University in Taiwan. And then he got his PhD in chemistry at University of Pennsylvania. And there he conducted research on semiconducting polymers with Professor Alan McDermott, who was a Nobel laureate in 2000. And I'll get into a little bit more specifics in the next few slides, but just want to highlight that there's been 7 Nobel Prizes in the polymer field. And so, it's really exciting that, Mike Chung has been able to, work in this area. And so, this is a, really big accomplishment. Professionally, after his PhD at Penn, he was a research scientist at the Institute of Polymers and Organic Solids at University of California at Santa Barbara with Alan Heeger. And so this was kind of a fun story. So while at Penn, Alan McDermott and Heeger, who was in the physics department, worked together. And then Alan Heeger left and went to Santa Barbara. And then Mike went there for 2 years as a postdoc and still worked on semiconducting polymers and the chemistry and the physics of these materials. From there, he went and worked at ExxonMobil, or I guess Corporate Research Exxon Company. And then he started as an associate professor here at Penn State in 1989, and then became full professor in 1993. You know, and as his independent career, he's done a really lot of work in fundamental chemistry of polymers, and synthesizing them, mostly polyolefins. So almost every polymer that we interact with today is a polyolefin. But now he's doing some really exciting stuff related to petrogels, where he's able to absorb oil from oil spills. And it's nice to see the transition from, you know, the pure chemistry to applications. And Professor Chung has been able to do that nicely throughout his career. And so he's authored over 200 professional publications, 2 books, 45 US patents. And again, you know, at his core, it's polymer materials chemist who's worked on semiconducting polymers, most recently polyolefins, from applications to gas storage and oil spill recovery. And what I wanted to do in the next few slides was just show some of these articles he had throughout his time. Yeah, and so as a PhD and postdoc, optical studies of pyrolyzed polyacrylonitrile, polythiophene. You know, if you're interested or at all familiar with semiconducting polymers, the model system is polythiophene. And so Professor Chung has done a lot in that area. And these 3 papers here just show, you know, the huge contributions he's made in this field in the heyday. And so, you know, he's been a real pioneer in this work, which is a really big field nowadays in polymers, semiconducting for organic light emitting diodes, and all the other types of things that are out there, organic photovoltaics. And so the next slide. When he first started here at Penn State, he made some really huge contributions in using borane chain transfer. So if you're ever familiar with polymer chemistry, one of the main goals is being able to control molecular weight and the distribution in molecular weight, and also chemical composition. And Professor Chung has done a really nice job with using this borane chemistry or metallocene mediated olefin polymerizations with boron to be able to make polymers that are hard to make and add chemical functionality that wasn't possible before this. And then lastly, some of the recent stuff he's done, again, this petrogel, which is really exciting material. I mean, you know, before these materials, it was extremely hard to recover oil from a spill. And so now Professor Chung has been able to take the chemistry again, make materials that will help, you know, in the future for maintaining or you know, recovering oil from these spills, and then reusing it and bringing it back. So it's not only can you absorb it, but you can actually use that oil. And you know, I don't have, this is the last slide, but I also want to bring up, you know, it's been fun discussing different areas of research with Professor Chung, especially in his gas storage. And so one of the big things he's doing now is making carbon materials from using polymer precursors for gas storage, which is a really big area now. If we're thinking about transitioning from oil, how do we have condensed gas? How do we make carbon fibers cheaply? And so, you know, I'd like to end that Professor Chung has been, you know, really influential in the polymer field from a chemistry and a materials perspective. Professor Chung has also been a really great mentor for me when I started here. He's really helped bring me along, at least in my lab area. And so he's been very generous with giving me lab space and just a good person to talk to about polymer chemistry. And so with that, I'd like to end.
Thank you very much, Rob, for the nice highlight of Mike Chung. Well, that concludes our webinar for today. Many thanks to all of the speakers. And a reminder that we will have a second session on Friday at 10 a.m. this Friday, May 28th, with another set of speakers and highlights. So thank you, everyone. I hope you enjoy the rest of your day and your week, as well as the summer.